I'm Sara Medhet, a PhD student under the supervision of Professor Dr. Farhan Says from Department of Electronics, Quaid-i-Azam University, Islamabad, Pakistan. Today I'm here to give you the presentation upon the topic Signature of Intermittent Transition on Dynamical Localization. Here is the outline of my presentation. First of all, I'm going to give a brief description of what was the main motivation behind choosing this topic, then coming towards what an optical lattice is, then explaining the experimental setup of our system and the governing Hamiltonian, then explaining the dynamical localization using the results obtained, and in the end, I would like to conclude my presentation. The main motivation behind choosing this topic was that the dynamics of ultracold atom in amplitude modulated and phase modulated optical lattice is an analog of an electron dynamics in a crystal under the influence of AC electric field. Cold atom in amplitude modulated optical lattice have shown intermittent transition, dynamical tunneling, and quantum revivals. Dynamical localization of cold atom in phase modulated optical lattice is the subject of extensive discussion both theoretically and experimentally, while in amplitude modulated optical lattice, it's still an open question. So in our present work, we will show the existence of dynamical localization of ultracold atom in an amplitude modulated optical lattice with harmonic confinement. Here is the link to our recent publication. Now, what an optical lattice is. An optical lattice is a periodic potential created by light-matter interaction. The resulting interference pattern can be used to trap atom in a periodic structure. These trap atoms resemble a crystal lattice and can be used for quantum simulation. As shown in the figure, you can see the optical lattice. Now, in our case, we have considered the cold rubidium atom in a weak harmonic trap, such that the initial wave packet satisfies the minimum uncertainty criteria. Now I did vertically turning on the lattice by slowly ramping up the intensity of the laser beam. The process has created a combined potential of optical lattice and parabolic trap. The Hamiltonian of the system consists of a kinetic energy term and a potential energy term. The potential energy term consists of optical lattice, the induced modulation, and the parabolic trap. Now here epsilon and omega m are the amplitude and angular frequency of the modulation respectively, and omega naught is the trapping frequency and v naught is the lattice depth. Now rescaling the Hamiltonian using the rescaling z is equals to kx and t is equals to omega tau. We get the rescaled Hamiltonian as this with the rescaled parameter as given below. The values of these rescaled parameters are taken from a recent experimental papers with lattice constant 457 nanometers and lattice depth 32, and the modulation strength in our case is epsilon equals to 1. Now dynamical localization in amplitude modulated parabolic optical lattice. Coming towards the main topic, firstly we will explain what an Anderson localization is. In 1957, Nobel laureate Philip Anderson suggested that certain material can suffer a sudden phase transition from conductor to insulator under a slight change in the amount of disorder in the material. Now here you can see that the inherent property of a metal is that the electron can move from one lattice side to another and is a perfect conductor. And the wave function is there in that case is as shown above. While as we introduce a disorder in the system, you can see that the wave function get more and more localized over the space. Now, in case of high-level disorder, Philip Anderson shown that it resulted in the localized states and the diffusive part halt and the conductivity is diminished and metal turns into an insulator. Now, coming towards what dynamical localization is. Dynamical localization has been previously understood as quantum suppression of classical chaos. It was predicted that a quantum particle exhibit diffusion following classical evolution till quantum peak time. Beyond this time, the diffusion stopped due to quantum interference effect. In 1982, Fishman shows that the phenomenon of dynamical localization in kicked rotor is similar to that of Anderson localization in solid-state physics. This led to the recognition that quantum suppression of classical chaotic diffusion of momentum of rotor in a dynamical version is a dynamical version of Anderson localization. The reference of the paper is given below. Now, in our case, we have the similar thing that the amplitude modulation is similar to that of a disorderness in the Anderson, in same as the disorderness in the Anderson localization. Now coming towards our results, first of all the variance versus time plot. Here you can see classically the red line, the system is diffusive and more dispersive, while in case of quantum mechanically, that's the green line. Initially the system follows the classical trend, while after quantum break time, the system is suppressive. Now, similar is the case in momentum space. You can see classically it's increasing, while quantum mechanically it's dispersed, it's suppressive. Now, this classical quantum contrast between in position momentum space is called leads to the dynamical localization. So the main theme behind this is that classically the system is dispersive, while quantum mechanically you can see that both in position momentum space, you can see that it's more and more localized as the time passes on. Now, in our case, we're going to have the dynamical localization both in position as well as in momentum space. Now coming towards the probability distribution. The probability distribution in our case, we can see classically, that's the red line. The system is showing a Gaussian distribution, while quantum mechanically you can see a localized behavior. The peaks here corresponds to the diffusion to the next lattice side. To get a more clear picture, we have plotted the log scale plot of the probability distribution in position space. Here you can see that classically it's linear on the both side and it's symmetric, while quantum mechanically that's the green line. You can see that it has an exponential drop. This exponential drops shows the existence of dynamical localization, that it is maximally localized to the first few lattice sites. And after that, you can see an exponential drops over here and here. Now, on the other hand, in case of momentum space, you can see classically it's a broad distribution, while quantum mechanically you can see that it's localized and has multiple peaks. These to get a more clearer picture, you can see the log scale plot, and here you can see that classically is dispersive, while quantum mechanically you can see the peaks. Now the peaks here correspond to the band structure, the localization of the amount of population transferring to the next lattice site. Now in our case, using the initial using the values we have taken, we can see that the maximum population resides in the zeroth band, and after that, first, second, and third bands are maximally populated, and after that, we can see a sharp exponential decrease. Now, to get a more clear view of that, we have plotted the band population versus time plot by projecting the time-dependent wave function on the block eigenstate. Now here you can see that for the case of zeroth band, that's the purple line, you can see that the maximum population resides in the zeroth band, and as the time evolves, you can see a dip and the population transfers to the next lattice site. Now, as the time evolves, you can see that it regains to the zeroth band due to interband transition. Similar is the case in the higher time. Now, as we have plotted the previous plots at t is equals tau is equals to 300, so we can see that at tau is equals to 300, the maximum population resides in zeroth band and then first, second, and third band. which is the similar view as you can see over here. So the maximum population resides in the real pen, and then first, second, and third, and after that we get a sharp decrease in the mm, population. Now this strengthens the presence of dynamical localization both in position and momentum space in our um, system, that is temperature modulated optical lattice. So in the end, I would like to conclude my presentation. Now here we can see that we have shown the dynamical localization first time in amplitude modulated optical lattice in the presence of harmonic confinement. Our system exhibit dynamical localization both in position as well as in momentum space, which make it different from other systems like phase modulated, which have dynamical localization only in momentum space. The phenomenon of dynamical localization is shown as a manifestation of interband transition for the first time, and in the presence of modulation, confining the band population mainly to the first three bands in our specific initial conditions. We've shown that the intensity modulation of the optical lattice introduced a disorder, same as in that case of Anderson localization, because the occurrence of dynamical localization is subject to the disorder strength, that which is amplitude modulation in dynamical system. Now, as you can see that for the case of Anderson localization, as you introduce the disorder in the system, you will see that the conductivity halts and the system get localized. Same in our case, when we increase the modulation strength, the system is getting more and more localized. Now, the experimental parameters used in our case are from a recent experiment, so it can be used. So we suggest that this phenomenon can be realized in the state-of-the-art experiment and can lead to newer understanding of the system. Now, coming towards the usage, these articulated atoms can be used in improving the precision of atomic clocks or as quantum qubits in quantum computers. Now, that's all from my side, and thank you for your attention.